In quantum mechanics, we say electrons in atoms are described by wave functions. But in chemistry, we usually talk about orbitals. So here's a question. What exactly is the difference between a wave function and an orbital? And even more interesting, how do orbitals combine to form the full wave function of an atom with many electrons? There is actually a missing link between them, and that missing link is electron configuration. Today, we'll see how electron configurations connect orbitals to the true many-electron wave function using one of the most important ideas in quantum chemistry, the Slater Determinant. Don't worry, we only need one example to understand everything.
Let's begin with the simplest possible atom, the hydrogen atom. Hydrogen contains only one electron, so its wave function depends on just one position, psi of x, y, z. And here something special happens. In hydrogen, the orbital is the wave function. Same object, same mathematics, same physics. Life is simple. But real atoms contain more than one electron, and everything changes.
Consider helium. Now the wave function must describe two electrons simultaneously. Psi of x1, y1, z1, x2, y2, z2. This is called a many-electron wave function. In principle, this function contains everything we could know about the atom. But there's a problem. Even for just two electrons, the wave function already depends on 6 spatial variables. For 10 electrons, 30 variables. For 20 electrons, 60 variables. So even if we could write the exact wave function, and usually we cannot, it would be extremely difficult to interpret physically. It would be like trying to understand a movie by reading all the pixels of every frame at once. We need a simpler description. And this is where orbitals enter the story. Instead of describing all electrons simultaneously, we describe them one at a time, moving in an average environment created by the nucleus and the other electrons. This gives us something called an orbital. Semi-rigorously, an orbital is a one-electron wave function describing how a single electron moves in the average electric field inside an atom. Orbitals are not the full wave function of the atom. They are its building blocks.
Here is the key physical idea. When we use orbitals, we replace the complicated motion of strongly interacting electrons with simpler objects that behave almost like independent particles. Physicists call these effective particles, quasi-electrons. A quasi-electron behaves like an electron, but already includes the average influence of the other electrons around it. So instead of solving one impossible many-electron problem, we solve several simpler one-electron problems. This strategy appears everywhere in physics. For example, vibrations in crystals are described using particles called phonons. Phonons are not real particles. They are quasi-particles that simplify a complicated collective motion. Orbitals play a very similar role for electrons inside atoms. And this idea works remarkably well. It explains the structure of the periodic table, atomic spectra, and most of chemistry. So now we understand the strategy. Orbitals describe quasi-electrons, but atoms contain many quasi-electrons. So we must combine orbitals into a proper many-electron wave function. And to do that correctly, we need one more ingredient from quantum mechanics. Electrons belong to a special category of particles called fermions. Fermions obey a remarkable symmetry rule. If we exchange two identical electrons, the wave function must change sign. Psi of 1, 2 equals minus psi of 2, 1. This property is called antisymmetry. It may look like a small equation, but it controls atomic structure, the periodic table, chemical bonding, and even why matter occupies space instead of collapsing. So this minus sign is doing serious work. Let's apply antisymmetry to helium. Both electrons occupy the 1s orbital. So we might try writing 1s1 times 1s2. But this expression does not change sign when we exchange the electrons, so it cannot be a valid fermion wave function. Something is missing. That missing ingredient is electron spin. Electrons can exist in two spin states, alpha, the spin up, and beta, the spin down. So instead of ordinary orbitals, we use spin orbitals. Example, 1s alpha, 1s beta. A spin orbital describes both where the electron is likely to be found and its spin state. Now we finally have the ingredients needed to build a valid many-electron wave function. To combine spin orbitals correctly, we use something called a Slater determinant, named after John C. Slater. For helium, it looks like this. Psi equals 1 over square root 2, determinant 1s alpha 1, 1s beta 1, 1s alpha 2, and 1s beta 2. Let's expand it. Psi equals 1 over square root 2 times 1s alpha 1, 1s beta 2, minus 1s beta 1, 1s alpha 2. Notice the minus sign. Now, exchange electron 1 and electron 2. Then, psi of 2, 1 equals negative psi of 1, 2. Exactly what antisymmetry requires. So Slater determinants automatically produce valid fermion wave functions. They enforce the rules for us, even when we forget to. Now something remarkable happens. Suppose we try putting two electrons into the same spin orbital, 1s alpha 1, 1s alpha 2. Then the determinant becomes 0. That means the wave function disappears, which means this state cannot exist. And this is exactly the Pauli exclusion principle. So the exclusion principle is not something we insert manually. It emerges automatically from antisymmetry. Quantum mechanics quietly enforces it behind the scenes. Now we connect everything. Instead of writing full Slater determinants like this, chemists simplify it like 1s alpha, 1s beta goes to 1s, 1s, goes to 1s squared. The last one is the electron configuration. They're simply compact labels describing which spin orbitals are occupied inside a Slater determinant. So when you see 1s squared, 2s squared, 2p squared, you are actually seeing a shorthand description of an antisymmetric many-electron wave function. That's a lot of physics hiding inside very small superscripts. There is one last twist. Real atoms are not described by just one configuration. Instead, psi equals C1d1 plus C2d2 plus C3d3, and so on. Namely, the true wave function is a mixture of several Slater determinants, the Ds. This idea is called configuration interaction. So electron configurations are not the full story, but they are the best first approximation, and they are powerful enough to explain most of chemistry. So here is the big picture. In hydrogen, orbital equals wave function. In many electron atoms, wave function equals combination of spin orbitals. Spin orbitals combine using Slater determinants. Slater determinants enforce antisymmetry. Antisymmetry produces the Pauli exclusion principle. Electron configurations are compact labels for those determinants. So next time you see something like 2p6, remember, you're not just looking at electrons in orbitals. You're looking at the symmetry laws of quantum mechanics, organizing matter itself. Thanks for watching, and I'll see you in the next episode.